Hello, today I will show you a few pieces of equipment of geotechnical apparatus. First of all will be the resonant column. Resonant column is the equipment which we are used to find the parameters for the geotechnical design when we are dealing with the dynamic excitations. The beginning of this apparatus was in Japan, when the geotechnical engineer have to solve the problem of earthquake and earthquake design, and they prepared some solutions which today we are calling as resonant column. As you can see here inside, in this white membrane, there is a soil sample, which on the top of this sample there is 4 magnets installed, and the top of the sample is squeezed or shaked by these magnets just to find the properties of the soil during the earthquake or dynamic excitation. The example of the dynamic excitation is, for instance, the highway traffic, which is sometimes can be very heavy. So we are applying excitation on the top of the sample, and then we are looking how far the sample and how long the sample needs to dissipate this excitation. Based on these measurements, we can find the such parameters like shear modulus, damping ratio, or resonant frequency. The resonant frequency is mostly interesting because with the resonant frequency we can find the frequency in which the soil will have the biggest strain. So during earthquake, for instance, when we have this kind of frequency, or during the traffic, this frequency when it happens, the excitation will be the highest, and then the damage to the surrounding buildings will be the most severe. Yeah, so that's what we are using, and we are using this equipment. Let's go to the different kind of apparatus, very traditional one. This is the triaxial apparatus, and triaxial apparatus is the basic test which we are using for gathering of the parameters. The most 2 common parameters which you can get from this equipment is the friction angle and cohesion. And we can do the triaxial test in 3 different modes. First one is consolidated drained, second consolidated undrained, and the third one unconsolidated undrained. These 3 types of tests are important and they are addressing 3 different cases in which soil can find itself. So basically our goal is to create the pressure by this water which is here in this cell, the pressure which is on the depth from which we taken the soil. And then after we apply this pressure, in case of cohesive soil, we are consolidating the sample. So we are waiting until the excess pore water pressure will dissipate, and then we are starting our test. Basically, from the practical point of view, the test is done in that way that this piston over there is penetrating through the soil. So we are applying the vertical stress on the sample, and we are observing how the soil reacts to this load. Usually, this type of soil are developing something which we are calling the shear plane. So we can see that the sample is shearing in one direction. This is the sign of failure of the soil. Based on the top force which is on the sample, we can measure then we can find the friction angle and cohesion. And so that's the basics of the triaxial test. Part of the triaxial cells can be equipped with the piezometer. This is this small thing, this line over there is the piezo element, which can deform in the way that we are want it. So we can create a wave which is traveling through the soil sample and is receiving by the other piezometer. Based on the fact that we know how high the sample it is and how much time the wave needs to travel from the emitter to the receiver, we can calculate the velocity of shear wave, or even with the velocity of the pressure wave with different kind of piezometer. These two parameters are enabling us to calculate very important parameter, which is shear modulus. Shear modulus is used for very advanced numerical modeling models, like for instance cam clay or hardening soil models. This is a cyclic triaxial apparatus. In this apparatus we can apply cyclic loading. This kind of loading is very important for studying the effect of the traffic of the machine working on the foundation which is supporting machines. Although also the electrical plant, wind electrical plant. In each cases we have something which we call quasi-static loading, which is repeatable motion and needs a different kind of test to study and to find the parameters for the design. In this triaxial cell over here we have the motor, which is applying the vertical stress, which is transferred to this piston on the sample, which is over here. We can load this sample with the frequency up to 5 Hz, which is representing most of the possible cyclic excitation which we can have in our environment. The most important fact here is to study in case of non-cohesive soil liquefaction, which can happen due to cyclic loading and developing of the excess pore water pressure. And in the case of the cohesive soil, the main topic which we are studying is the developing of the pore water pressure, which then can lead to soil failure or to the rooting. So if you see on the pavement outside on the road the deformation of the surface of the pavement, this is the rooting and this is the effect of the cyclic loading, and this effect is due to accumulation of the plastic strains. This equipment is exactly the answer to find the solution to these problems. This piece of equipment is already installed, but we done it exactly for you to show you what this equipment is able to do. This is the sample which we are placing here in the apparatus, and the sample, what is interesting, has hole inside here. And this hole is very important because if we are placing the sample over here in this apparatus, we can apply two kinds of stresses. First one is outside of the sample, and the second one is inside of the sample. So we have two different kinds of stresses which are acting on the outer and inner cell. Then we can apply cyclic loading, and we can also apply torsional shear. So we can model exactly what is happening in the soil during, for instance, stability loss, when the soil is subjected to the different direction of the principal stresses. And as well, we can apply cyclic loading, so we can model exactly what is happening in the with the pavement during the high traffic loading. These studies will help us to find the solution for the designers to design better and more sufficient and sustainable roads in the future. This is the unsaturated triaxial apparatus. This piece of equipment is designed to study the effect of the unsaturation on the soil strength. The common triaxial apparatus is able to find the parameters like friction angle or cohesion only for the soils which are fully saturated. So the voids in the soil are fully filled with the water. But in the common design experience and practice, you will find that the soil on the top is not always in full saturation conditions. So when we are building slopes or different earth structures, we have to account this in our design process. And this apparatus is able to create the unsaturated state. So not all voids are filled with the water, but also with the air. This can change, and this is changing the friction angle and cohesion of the sample. There is a design especially for it, the pressure controller. Here you can squeeze the air, and you can place this air in the soil sample through these installments. So therefore we know what is exactly the volume of the air inside this sample, and we can measure the friction angle and cohesion of the soil with this in this precise state. Then we can update our information about the strength parameters and be more sure about what we are going to design. This is permeability apparatus, and this piece of equipment is used for the studying the coefficient of permeability. Usually with this cohesive soil have very low coefficient of permeability, so we need the equipment which is able to find the value within the short period of time. And here we are using the falling head method of measuring coefficient of permeability. The basics of this test is to apply higher pressure on the bottom of the sample, which is causing the water to flow through the sample to the top. Then we are calculating the time which the water had to take to flow through the sample, and finally we are able to measure the coefficient of permeability. This type of test is able to shorten the time of calculating the coefficient of permeability by 10 times even. So it's very reliable and very good method for cohesive soils. This is the automatic eudometric test, which is used for finding the deformation parameters, the strength parameters, and in which we can find the eudometric modulus, for instance, or we can find the per-consolidation pressure. The purpose of this test is to measure how the soil will respond to the vertical loading, but in the case when there is no possible way for the horizontal strain. So as you can see, this is the metal ring which is preventing soil to deform in the horizontal direction. So when we are putting this top cap on the sample, then during the test the top cap is compressing the soil, and based on the fact that we know what is exactly the force which you are applying on the sample here, and based on the knowledge of the displacement which is occurring on the sample, we can measure the modulus coefficient. We can measure the coefficient of consolidation and compression modulus. This piece of equipment is used for the measuring of heat conduction, coefficient of heat conduction, and this is the needle, this is the probe. and we are using this probe to measure how fast the temperature is spreading across the sample. So we have two thermometers here. One is in the top, second is in the middle, and the third one is outside of the sample. And we are placing this needle inside of the sample. So we are taking the needle inside, and then the software is measuring the time in which the heat is spreading. Based on this measurements, we can find out the coefficient of the heat conduction. We can measure how fast the heat is spreading to the soil, and then we can find then we can design the heat exchangers, for instance, for the ground thermal solutions. So this equipment is used for the ultrasonic pulse velocity measurement. We are using this stuff for the measuring the vertical, the shear wave velocity and the pressure wave velocity. These two sensors are used for the measuring the pressure wave velocity, and it's used mostly on the in geotechnical engineering on the stabilized soil samples. So this is the piece of stabilized soil. This soil was stabilized with the concrete and the dispersed reinforcement. So when the sample is ready to be tested, we are placing it all in this horizontal direction, and then we are putting these two sensors like this. Then the dedicated software is taking the measurement, and we can find the velocity of the pressure wave. So this is the pressure wave, and the second option is to measure the shear wave. Shear wave is measured with these two sensors. So this is the first one, this is the second one, and we are doing exactly the same. So we are placing this stuff over there. We are squeezing a little bit just to be sure that there is a contact between the sample, and the software is measuring the shear wave velocity. Based on the information about shear wave velocity and pulse wave velocity, pressure wave velocity, we are able to calculate the shear modulus and Poisson ratio. So that's basically the two things that we are need for the design of the stabilized soil.